So I've just written down on the board where we left off. We had found linear approximations for x prime and y prime. Okay. And so here are the results for the particular example that we're working with. I should just point out, in the last video, I think I was still writing this as x minus x naught. That was kind of silly. X naught is -1/2, so I should have just plugged that in. Same thing here. I think I was writing y minus y naught. Y naught is 5. I should plug that in. So I did. Okay. So this is fabulous because we've got this linear system. The problem is the type of linear system we're used to working with is the type of linear system that's homogeneous as well as constant coefficient. Now this is constant coefficient. If I look at this, I've got x prime is about equal to x plus a half y minus 5/2. So that would be x, plus 1/2 y minus 2. Now that's constant coefficient, but it's not homogeneous because I've got this function of t. It happens to be a constant function of t, but this extra function that I'm adding to my x's and y's. And that means there's no way I can represent it this way, because any system like this has the origin as an equilibrium point. But if I plug in 0 for x and y, I don't get 0. So the origin isn't going to be an equilibrium point here. There's no way I can represent it, at least not in the xy plane, this way. Now, here's the issue. My equilibrium point in the xy plane is here at -1/2, 5. The only way I could have y prime equals ay having an equilibrium point there would be if there was an entire line of equilibrium solutions that passed through that point. And that would do a lousy job of approximating the system that we started with here, because we determined that that has 4 equilibrium points, not an entire line of infinitely many equilibrium points. So what I'm going to do is I'm going to pick things up and I'm going to move them. I'm going to do a change of variables to the UV plane. I'm going to pick that point up, and I'm going to move it here, and I'm going to put it smack dab at the origin. I'm going to do that by letting u equal x minus x naught, which in this case is just x plus a half, and v equal y minus y naught, which in this case is y minus 5. So I'm just picking it up and moving it. So 0, 0 on this picture corresponds to -1/5 on this picture. Okay. And I can now start talking about u prime and v prime. U prime at the origin is going to be exactly the same as x prime at x naught, y naught. Because I'm not just picking up that point and moving it, I'm picking up my entire phase plane and just moving it. An analogy from single variable calculus. If I had the sine graph, I know that has a horizontal tangent at height pi/2. If I were to move that sine graph over a little bit, now there's a horizontal tangent at the location where that point got moved to. So if I'm moving an entire graph, the derivative that was associated with that point is still associated with that point. It's just now in a different location. Okay. So I've created this new system, u prime v prime. Okay. Notice this is just, this is take 2 of this video. I had previously labeled that was u and that was v. So what I'm getting here then in this new system, I'm getting u prime is u plus 1/2 v. V prime is -20u minus 5v. That's awesome. That's saying that u prime v prime is just this matrix 1, 1/2, -20, -5 times uv. And I'm going to call this matrix J. We've usually been calling our matrices A. I'm going to call that J because it's actually called the Jacobian matrix. Now, those of you in 3C, we've seen or we will see, depending on where we are in that class, something called the Jacobian that is the determinant of a matrix. Okay, I'm going to try to be good about always calling this the Jacobian matrix rather than the Jacobian. The books are using the terminology slightly differently. This textbook is referring to this matrix as the Jacobian matrix. The analogous situation in 3C, we would talk about the determinant of that matrix as just being the Jacobian. Okay. All right. What's important is that that gives us this linear system. This matrix consists of basically just these four partial derivatives. Okay. Turns out that matrix is, in fact, the derivative of the function that took me from xy to x prime y prime. But we just needed to know how to build it by putting the appropriate partial derivatives in the appropriate place. Okay. So, now we've got this. What I'm going to do is I'm going to classify the origin, which is the only equilibrium solution for this particular system, because notice the determinant here is not 0, so 0 is not an eigenvalue. Okay? I'm going to classify the origin, and I'm going to make an educated guess that the equilibrium point -1/2 5 behaves in a similar way, because I'm expecting that the linear approximation actually approximates the system, so that what I get here will be similar to what I had there. So let's take a look at this. Now it is important that you remember to change the names of your variables, because here 0, 0 is the only equilibrium point. I think with this particular system, we did have that the origin was an equilibrium point, but often you'll have a nonlinear system where the origin isn't an equilibrium point. So it would actually be wrong to say x prime, y prime. I mean, it is wrong even here to say x prime, y prime equals the matrix times x, y. Okay, so if I want to take a look at this, I'm going to take a look at j minus lambda I. Okay. So j minus lambda I would be 1 minus lambda 1/2, -20, -5 minus lambda. That's going to be 1 minus lambda times -5 minus lambda, minus a negative, so plus 10. So let's see, that's lambda squared, plus 5 lambda minus lambda, so plus 4 lambda minus 5 plus 10. So that's lambda squared plus 4 lambda plus 5. So my characteristic equation is lambda squared plus 4 lambda plus 5 equals 0. That does not factor. It does not factor. So I'm going to use the quadratic formula. Lambda is going to be the opposite of 4, plus or minus the square root of 16 minus 4 times 1 times 5 is 20, all over 2. It's -4 plus or minus the square root of -4, all over 2. That's -4 plus or minus 2i over 2. I'm going to just factor out a 2 on the top, so that's -2 plus or minus I over 2. Those cancel. I get -2 plus or minus I. So we've got complex eigenvalues with a negative real part. So I know that the origin in this linear system is a spiral sink. So I'm guessing that the equilibrium point -1/2 5 in the original system behaves kind of like a spiral sink, so that solutions that are nearby are going to approach that equilibrium solution, but by rotating around it first. Okay. So what I'm going to do is I'm going to stop this video now. The next video, I'm going to just show you a screenshot of DE tools. And we're going to compare the phase portraits for our linear system here in U and V and the phase portrait that we get for the nonlinear system that we had in X and Y.